Okay, welcome to our Bucky call for the weekend of November 29th and 30th. Anne is doing granddaughter duty, and Manu hasn't showed up yet, but hopefully he'll arise and shine and catch us. So, um, Fred, how are you feeling, and what do you anticipate getting out of? I don't really know where we are before we start. When I left off last time, oh, I just pulled up the wrong book. I left us off on page um,
19.
215 um, on the subsection called Mite. Does anybody
Yeah,
know
that's
where
it. That's 219 on my book, but it's a mite. Yes.
it's the Mite chapter? Okay, good. So we know where we're going to start then. That's a
Okay.
wonderful thing. So let's continue. Fred, how are you feeling? And what do you anticipate getting out of tonight?
I'm feeling, I have mixed feelings. I'm feeling sort of relieved that finally a date has been set to to spread Lucy's ashes at sea. It's next week's Friday, on the 5th. And I'm also feeling, how to say, a little bit of dread. It should be like a closure. I was expecting it to be like a closure or something like that. Maybe it will be, but I'm dreading it a little bit. I wonder if that ceremony or event would be bringing me down a little bit, or if it will be like a relief. I don't know. I was expecting it to be a relief, but now I'm dreading it. So that's how I'm feeling. And I've got to go this afternoon to finish the paperwork with the administration. They called me, they need more copies of official documents, so I'll go do that this afternoon. And for some reason, they're working on Sunday afternoon. And my expectation is to learn a little bit something as usual. If I just learn a little bit, then progress, a little bit progress is progress. So Lee, fashion forward Lee, how are you feeling and what is your desired takeaway today?
I'm feeling real achy, sneezy, coffee, and I got an infection in my eye, but I'm anxious to listen to all of you so that I can learn about me. Is that what it's called?
Mite.
Mite, like the mite coin long ago during Jesus's time. Ah, close. But um Joe, how are you feeling and what do you want to get out of this evening's talk?
Well, it's getting colder here, that's for sure. So there's nothing to really kind of um not a lot of outside time, let's just say that. And so that's unfortunate. Uh, but I enjoy the seasons. So, but no, I think it's going to be interesting getting into this particular chapter, actually, or section, I would say, um, of the book, and I think that we've covered one of the things that major things that we've covered here every weekend, and almost I would say is the maximum use of space. And so I think with might, that's what I gather is really one of the more important parts of it. So um, yeah, no, I'm looking forward to getting into that, and it'll be some good intellectual stimulation. I haven't had a lot today, so Richard, Richard, how are you feeling? What do you want to take away from today?
Oh, yes. Good day to everybody. Well, as I was saying earlier, I'm feeling a bit cool with our weather, um, and but somewhat rejuvenated because today I got reconnected with our World Weavers meeting group that gets together every second Saturday, and I'd missed the last several, partly because I was out of country or in a different time zone, and with the time changes 2 weeks ago, thereabouts, I got all mixed up and missed the meeting, much like I did on this one a couple of weeks ago. So yeah, I'm wanting to get more out of this, the combination of the tetrahedron and the octahedron, and more into the understanding of the role of the square and the cube as sort of flexible elements that keep the dynamism of the tetrahedron and the octahedron sort of in motion or in dynamics. And also helping us move away from the preoccupation that we've had as a society or nations over the years of the stability of the square or the cube, as if they're the benchmark sort of geometric figures in our societal lives, and we've all been sort of dominated by that in many ways. And so this is opening up the dynamism of the structures we're talking about, and the kinds of fuller explanation that Amy Edmondson is trying to convey when she wrote her book several years ago now. Yeah, so I'm looking forward to this dialogue in terms of this focus on mites. And Steve, how are you feeling? What's your expectation for today?
Well, I'm getting over my cold, but I still have a cough and a runny this or that. And I keep trying to sing, and it doesn't seem to help. So, but I'm getting over it. I'm excited about what we're doing between cosmometry and Wednesdays and this book fuller explanation on the weekends. But yeah, just when I think I don't understand it, I remember this is about topology. And then just when I think now that I understand it's about typology, we are now in chapter 13 of this book. Chapter 13 is the heart of the matter, A and B quantum modules. And I'm going to read you something that I think is only fair because we haven't been here for a while, and I think it would be really helpful. Let's see here. I'm trying to. Okay, that was the wrong. I'm still getting used to this system. So here we are in. This is where we're going to start reading, which for me is at the bottom of page. It's at the bottom of page 219 in my book, but it is the bottom of page 219 of this PDF. So that's really nice. So, but if I go to, I think it would be helpful to read on page 213, which is the beginning of this chapter. And it's not going to operate like cosmometry. So there's 218. We're going to go to page 213. And right at the bottom of page 213, it's going to say something that I think is going to be pretty helpful. So I have to go up a couple more. Oops. Okay. No? Yeah. 214. One more, 213. And it's talking about A quanta modules. So this chapter is about A quanta modules and B quanta modules. And the A quanta module, this is the highly symmetrical friend, the tetrahedron. It's the A quantum module. The fact is that its four faces are equivalent presents the first opportunity for subdivision, resulting in 4 equal parts. Each quarter tetrahedron encompasses the region from a center of gravity, CG, to a face. And talks a little bit about that. And then, am I on page 213 yet? Oh no, that was at the beginning. So here we go. That was, I want to read you at the bottom, before we get into that IA module, because it mentions LCD, and I thought this is pretty important. The final asymmetrical so here it is. Necessity thus leads us to Fuller's A and B-Quanta modules. The missing element in our IVM analysis is a way to handle redundancy. Symmetry, the degree to which a system looks exactly the same in different orientations, is a kind of structural redundancy. The tetrahedron, the octahedron, and their various combinations all have a degree of symmetry, and now we intend to go to the root of it. How? By subdividing symmetrically until we can go no further. Now, if we're talking, if we're talking topology, and we're talking about fractal or self-similar times of parts of a thing, we keep subdividing that part until we can go no further. That doesn't sound very topological to me. As long as a system exhibits some degree of symmetry, it can be divided into identical subunits, which can be put together to recreate the original system. That sounds very topological to me. Ergo, the system was redundant. Through progressive subdivision, we can locate the minimum subunit of any system. This final asymmetrical module, I don't know how we went from symmetrical modules to finally to an asymmetrical module. So maybe you guys can explain that to me, or at least
the way you subdivide. Can I answer your question?
Okay, go ahead.
Okay, you subdivide on each symmetry you find into 2 elements that are identical because of symmetry until you can't anymore. And I think, and once you cannot subdivide anymore because there's no more symmetry, then that's where you stop, and then that's where you find a quanta module, which is the quanta would be the integer, the unit that you cannot subdivide anymore.
Okay, and that says this
And I think your confusion about where does it stop is because you are trying to link these subdivisions to the concept of fractal. A fractal is self-similar structure at every scale. That is, you would always find a symmetry that you could subdivide a fractal.
Exactly. And if I take a tetrahedron and I subdivide it symmetrically until we can go no further, that doesn't make any sense to me. As long as the system exhibits some degree of symmetry, it can be divided into identical subunits. So, okay, I get that. But then it says ergo, the system was redundant. Through progressive subdivision, it doesn't say anything about asymmetrical, we can locate the minimum subunit of any system. This final asymmetrical module, I just don't know how I get to a final asymmetrical module, but this is the point.
The last time you subdivide your system, it gives you 2 systems that are no more symmetrical, those that do not have symmetries anymore. And then you can no more subdivide following the rule of using a symmetry to subdivide.
But I don't understand how we do that, because I can take a tetrahedron and I can subdivide it forever, as long as I keep subdividing it on the halfway on each of the radii, on each of the edges. But somehow, and this is the point that I want to read, this final asymmetrical module, or least common denominator, LCD, because LCD is going to appear in this next reading a lot. So I thought it was important to remind myself, and hopefully you're interested too, that the LCD is what's going to be called the least common denominator. It contains the geometrical data needed to reconstruct the whole system. I don't know how we went from symmetrical to asymmetrical to the least common denominator, which is asymmetrical, and yet it has information for the whole system, which sounds like a fractal to me.
The
Doesn't a fractal have?
LCD, when you do LCD decomposition, you take a number and you divide it by its prime factors, and then you obtain a sequence of prime numbers which can be repeated. It's not a set, it's a sequence. Like 2, 2, 3, 3 would be 2 times 2 is 6, times 3, 18, times 3 is 54. So once you have the quantum modules, which would be like prime numbers, and the LCD sequence, the subdivision into prime factors, then you can reconstruct the whole structure from the sequence and from the individual units.
Right.
Does it make sense?
No.
No.
So I'm going to read this last sentence because it's, and then go to the next page, and then that sets us up for the Mite thing. No, because it doesn't make sense because we've been dividing symmetrically all along until we subdivide until we reach an asymmetrical unit. Well, I don't reach an asymmetrical module unless I've been subdividing asymmetrically in my mind. I can't subdivide symmetrically and end up with an asymmetric module. But somehow this says we can. And I want to finish reading this sentence and maybe you can explain it to me then.
I think you have to keep reading with it, Steve, because I think that this gets into how things are similar but the same.
Well, it says here we find
in the A and B, when she gets into A and B. So if you keep going and keep reading, you're going to see
where we're leaving A and B behind here really fast. We find the LCD by subdividing a polyhedron until we reach the limit case, that is, a module that can no longer be split into similar units. See, then it talks about A modules, A quanta modules, then it talks about B quanta modules, and then it talks about the energy characteristics. Progressive subdivision has left us with the legitimate metric quanta, final packages, which cannot be split into equal halves. I just don't understand how we get there. And then finally, we read down further until we get to mites, which are right here. And that's where we're going to start reading tonight. And the reason why I wanted to read what I read is because it says, next we apply our LCD analysis. So I looked back to see what LCD analysis was, and that's why I've read those sentences. So I hope I haven't confused anybody. And I hope that what I just read was helpful to begin this section. I'm ready to begin here if everybody else is ready to go. If you want to try and rescue me, I'm open for it. But I don't believe I'm rescuable.
Well, I'm of two minds on that. One is you say, I'm stuck. I don't understand what happened. And then you say, let's forget about that and continue.
Well, I'm confused, as I've stated, about the symmetrical subdivision
Okay.
until we end up with an asymmetrical module. I don't understand how you do that.
Okay. I think the solution is that you stare at it until you understand it.
And I think that's what I'm going to have to do.
Yes.
And rather than torture everybody, let's continue.
You need to take a tetrahedron and stare at it or play with it. I mean, if you can make a construction and follow the drawings on the book and see if you can get to the point where you find that you can no more subdivide because you've reached an asymmetry.
Well, the trouble is that all of my polyhedra have equal radii, and I keep subdividing them in the middle. I've never not subdivided a polyhedron in anything other than whenever I've subdivided, I always have equal radii, and I divide them in two. So, but somehow by subdividing, I get to an asymmetrical module. So I will stare at it.
The way you subdivide, you have to start from the center of gravity.
Aha.
and then you have to subdivide from there.
There we go. That's how I get
And explain,
asymmetrical.
and it's a different way of subdividing than the one you used to, you have in your mind. So
Exactly.
I suggest we keep going as you suggested, but but my suggestion is that you take a moment, you are well rested and well fed, and stare at it
I'm
until
going
the
to.
solution occurs.
And your clue about the center of gravity, which she actually called the CG, and I read that earlier, is the key. Because when you go into a center of gravity, you're no longer talking about the edges
Yes,
and subdividing edges. You're talking about subdividing the module, the
yes.
figure from the center of gravity. Perfect, Fred.
The process of subdividing is important to understand it before you start to process
Right.
it. It's easier to have a construction to play with than to do it in your mind.
Yeah.
And you can do it both for the A module and the B module, both for the A and B modules. Uh, I'm sure you will see it, and you will it will turn the lights on after you
Well, you just reminding me about the center of gravity. That turned lights on for me. So now
okay,
I know better what to stare at.
okay, cool.
Wonderful. Okay, good. Let me see how far do I go here? 22. Got to get back to there's 21. So that's probably 20. So here's 19. Okay, good. All right. I'll read this as long as I'm not distracting anybody. I'll read this page and then somebody else can read if they like. Mite. Next, we apply our LCD analysis. I'm going to keep center of gravity in mind to the IBM. The procedure calling for progressive subdivision is in search of the minimum repeating unit, comes to an end with a unit that we can no longer uh, be symmetrically subdivided. As before, we seek the smallest system that can be duplicated to recreate the whole IVM, a microcosm containing all the ingredients of the macro array, which I think is quite fractal istic, right? There's some fractalism to this. So anyway, having already split tetrahedra into equal quarters and octahedra into eighths, we skip directly to a unit consisting of a 1/4 tetrahedron and a 1/8 octahedron, back to back, sharing an equilateral triangle face. This unit, which connects the geometrical centers or centers of gravity, of which you pointed out, Fred, thank you, of any adjacent tetrahedron and octahedron in the IVM, exhibits the same threefold symmetry as its two triangular pyramids taken separately. Final subdivision thus yields six equivalent asymmetrical tetrahedra, the three positive and the three negative, in figure 13.4. And here we are in 13.4. And there are three positive and three negative. And this is the LCD, the lowest common denominator of the IBM, and it is a mite.
Mm.
Cool. So I am getting glimpses of this, Fred. Thank you very much. Anybody else want to read here?
I think you should set aside fractal for the time being.
Okay, I'm going to. And I'm going to be thinking center of gravity.
Yeah, because and you're completely correct on that. Fractal would be subdivided to infinity. There would be
Right.
no moment you get to a asymmetrical.
Your center of gravity was an absolute ding. It was a bell for me. So that's such a good starting place. Okay, good. I can read this one too. Um, as the smallest repeating unit of the IBM, this system is the minimum space filler, thus inspiring Fuller's term MITE, minimum space filling tetrahedron. That's what MITE means, minimum space filling tetrahedron. Well, I almost see a tetrahedron there. I
Mm.
guess this is an irregular tetrahedron here, A.
Yeah.
Here's another one, A, and here's another one, B. And maybe these two are labeled A because they're equivalent or symmetrical, where this one's not symmetrical. Maybe that's the
Actually,
case.
there's A quanta and B quanta.
Aha, as in
Yeah,
the previous part of the chapter. Thank you, Fred.
yeah.
A collection of A modules cannot,
And excuse me, sorry to interrupt you.
no,
They
perfect.
are A quanta and B quanta, and in that drawing, they come into, you need two A's and one B
Exactly.
to finish the construction, and that's where LCD comes in. LCD would be in this case uh, would be similar to a ratio of how many of one and how many of the other one.
Cool. Really good. A collection of A modules cannot fill space. They can only make regular tetrahedra. Notice the right angle here. These two are labeled A's. The skinny irregular B's cannot even create a symmetrical polyhedron by themselves, let alone fill space. The Mite is the LCD of the omnisymmetrical space-filling matrix and therefore is the minimum case, the first all-space filler. And he quoting Synergetics 954.09, we find that the Mite tetrahedron to be the smallest, simplest, geometrically possible volume, field, or charge, all space-filling module, or the isotropic vector matrix of the universe. I think that Manu would understand that really,
Yeah,
really
that's an
well.
interesting point, actually. Just
Yeah.
something else I've been learning about, um, how that may relate, but I'm not sure yet.
Okay. Well, if you get any eyes, speak right up.
I was thinking it has to do with energy. Um,
Yeah.
so, but I'm not sure if it directly applies to like something like 0 point energy yet.
I'll finish this page.
Wait,
Well, go ahead, Fred.
yes. There's an object of which I forgot the name, but I can't find it. There's an object that has been discovered maybe 10 years ago, whose it's a volume, it's a 3D object that cannot be subdivided into tetrahedra. And that was a discovery. And up until that moment, the conjecture was that not every space, not every shape could be subdivided or filled by tetrahedra, but we did not have a proof. Now we have a proof that there exists shapes that cannot be filled by tetrahedra. So when I look at the moment Bucky wrote his books and did his research, and the moment Edmondson wrote her books and everybody studying Bucky wrote that was everything is prior to the discovery. And I do not know. I did not contact the author or the discoverer of that shape to ask if it could be filled by a mite. I cannot check it by myself because my 3D abilities are infantile. I just cannot see in 3D. But I would be interested to know if that has been confirmed that the mite can fill all space, or that there exists shapes that cannot be filled by mites. That would be an interesting thing to find out. Maybe Richard, through your study group, you know that.
Do you know of anything like that, Richard? Let me just say before Richard unmutes and talks, prompted by what you said, Fred, I found a Schönhardt polyhedron is a shape that cannot be filled or tetrahedralized with tetrahedrons without adding extra vertices. While regular tetrahedrons can't fill space on their own, they can be used in combination with other polyhedra like the octahedron or a disphenoid, which can tile space on its own. And then it lists a bunch of polyhedra that can be tetrahedralized, but the one that cannot be is the Schönhardt.
Can you
Schönhardt.
put it in
I'll find it
chat,
and
please?
I
Yes.
will. I'll put it in the chat.
Actually, in many applications of computational geometry, computational geometry is use of computers and geometric algorithm to solve all sorts of problems. Triangulation in 2D is a very important process. That means you take a 2D shape and you can triangulate it. I mean, cut it into individual triangles. And this leads to a lot of applications because it simplifies things to deal with triangles instead of dealing with other things, because triangles are inherently flat. There's no curvature to a triangle. You take 3 points, 3 points define a plane. So inherently the structure is flat. However, it was a big issue to find, to be able to prove one way or another that 3D shapes could be tetrahedralized, subdivided into tetrahedra. And this has been proven that it cannot be done.
Cool. I'm pasting what I just read into the chat right now.
Thank you.
Richard, did you have a comment?
No, I don't. The other group does not have that answer. If they do, I don't have it embedded in me yet.
Okay. I'll do a bit of research. Thank you, Steve. That's a good starting point to have that. I'll do a little bit of research, and if need be, I'll contact the author of the papers that first discovered this shape and ask them if Mite composed of quanta A and quanta B could fill the space or not. That's an interesting question for me. Thank you.
Beautiful. Okay. Continuing this page, and I'll finish off and turn it over to somebody else. Knowing that the mite encompasses the asymmetrical units of both the tetrahedron and the octahedron, we can identify its constituent A model modules and B modules. The tetrahedron contributes an A module, while the adjacent octahedron adds both another A, the mirror image of the first, and B, for a total of 3 equal volume modules. The positive and negative A's are in balance. I think here comes what just happened. I've got too many buttons going on. I think it's yeah, Manu's joining us now. Okay, good. The tetrahedron contributes an A module while the adjacent octahedron adds both another A, the mirror image of the first, and a B for a total of 3 equal volume modules. The positive and negative A's are in balance, and the solo B can be either positive or negative, thereby determining the sign of the whole mite. Like A modules and B modules, mites come in one of two possible orientations. See figure 13-5. This is figure 13-5, and this demonstrates the two orientations.
Interesting.
This orientation is a repeat of chirality. That means left hand, right hand. No matter how you manipulate your left hand, you can never make it match the left hand.
This is the chirality or the chiral.
Yes.
Yeah.
Chirality.
Chirality. And that's how I say it. I'm sure it's not the only way it's said. But we've talked about chirality a little bit on a couple of occasions.
Yes.
And chirality in molecules is interesting because you can have a molecule of protein, and Fred, you can correct me on this if I'm wrong, and you can create a chiral molecule and it will have no effect at all unless it has a disease. That some diseases have left and right chiral molecules. And they're just getting into this idea, and they think that maybe even studying more about the chirality of proteins will lead to discovery for more cures for diseases. That's the podcast that I saw a while ago.
Yes,
Yeah.
that's correct. And you don't have to go through huge molecules like proteins. Glucose, which is a glucose, the sugar, the glucose is a very small molecule, and it has a L and D. It has a chirality
Cool.
property, and one of them makes you fat, and the other one has no effect.
Uh-huh.
Also,
Certainly.
I don't know.
I went crazy for a while, so let's see if I can catch up real fast. Manu, how are you feeling and what do you anticipate for today? Welcome.
Good morning, all. I'm just happy to be here and happy to be with you guys and on the train. So I'm listening.
Wonderful.
Yeah.
Okay, I got us to the page. This is the A and the A and the B. Modular decomposition of Mite. A is orientation of Mite. That's up here. And B is the unexpected mirror plane in Mite.
Hmm.
I'm happy to continue to read unless somebody else wants to.
I can do it.
Okay.
A mirror plane would be a plane of symmetry.
But it'd be chiral, wouldn't it?
Yes, because it's mirror. It's if you put your left hand in a mirror, you see your right hand.
Yeah, exactly.
Unless you're using your computer camera as a mirror, because in that case, it removes the chirality.
Yeah. Yeah, interesting.
I'm saying that because rigor in the use of vocabulary when you describe mathematical objects is important. And we've been talking about symmetry, and suddenly we talk about mirrors, but a mirror plane is a symmetry plane.
And they're chiral.
Yes.
Cool. Want to go for it?
It's just a note that I was thinking about in the week. Is my mic on?
Yes.
Whenever you go in a division below 60 degrees, you're going to have these mites. If you divide any angle in parts that are less than 60 degrees and symmetric, of equal part, you're going to have them. If you take an equilateral triangle like this, and you take a plane that goes through one apex and the opposite face perpendicularly, you're going to have mice.
Okay. Are you
Fred,
complete?
am I correct, Fred?
No. No, Mite is not a subdivision. Mite is a construction from quanta A and quanta B.
Yeah, I'm just saying that you're going to have two things. You're going to have chirality if you do it that way.
Yeah, but a mite is a very specific object that we just spent half an hour describing with the book.
Okay.
It happens to have the property of being chiral, and that what you're saying is that you get a chirality when you follow the process you described to divide a triangle, but that doesn't give you a mite.
Now, I'm just saying that if you have anything that is symmetric in regard to the vertices, all the vertices, especially a tetrahedron, and you divide it using one apex and a diagonal at the base, not the diagonal
Perpendicular.
yes, a
A plane of
perpendicular at the
symmetry.
base, yes,
Yes.
which will be a diagonal in respect to octahedron. You're gonna have a mite. That's what I was saying, and I ask you if it's correct.
It is incorrect.
Okay.
Well, and this is showing the right angle that you're talking about here, Manu. This is showing the
you look-
right angles. This is
if
the
you look at-
AA. Go ahead.
If you look AAB, Manu, the AAB means it's least common denominator decomposition of the mite. That is, it's quanta A plus quanta A plus quanta B.
And the quanta A are chiral, the quanta A are mirrors.
Okay, I see, I see.
Okay, so
Mhm.
if you take a tetrahedron and subdivide it, you cannot get a mite. You can get a chiral object, an object that has a property of being chiral, but you cannot get a mite. A mite is obtained from two different subdivisions of the tetrahedron, giving you subdivision into quanta A and quanta B that have the same volume. And if you reassemble two A modules and one B module, you obtain a mite. And then there's a complication of quanta A and quanta B can be negative or positive depending on their chirality also.
To
Okay.
reaffirm what Fred was just discussing, here's another picture of the same subdivision showing the two A's and the B. And then that double anus and Bnus is also described in these pictures here, in this figure here. There's your double A and your B. Here's the double A and the B.
Okay.
Cool. Joe.
Our starting point, Manu, was that of how do we subdivide, and it was from a question from Steve, that had difficulties to see how could we subdivide tetrahedra and get to a point where we get to asymmetries, to an object that doesn't have symmetries anymore. And so we discussed about that first, and then we talked about those subdivisions start from the center of gravity, not from the edges or the apex, and that's been the underlying theme of our discussion so far.
Okay.
Oh, that was a big light turn on for me, was to go from subdividing at the edges and subdividing from the center of gravity. Big time for me. Made a big difference.
Okay, go on. I will catch up.
Okay, good.
Sure.
And did I go too far? Where the heck were we? Maybe we're right here. This is where we are.
Yeah. We just finished that other
Okay,
part,
good.
quote from Synergetics, and then you went read to the end of the page.
Oh, do you want me to read to the end of the page? That's wonderful.
No. I can pick it up from here.
Okay, good. You can pick it up from here. Here we go.
I'm giving this a shot. I've been having serious problems with my eyes, so I'm trying different types of glasses. So
Okay, wonderful.
So we'll see what happens here. We
We'll
cannot
be
fail.
your guinea pigs.
Let's say, yeah. Cannot fail to comment on another 2-to-1 ratio just displayed by the minimum space filler. As suggested by this discovery, it turns out that there must be 2 A modules for every B module in any space-filling polyhedron. We shall see how this rule applies to our familiar candidates below. And once again, Loeb's contribution provides a more thorough analysis of the phenomena. Appropriate examples will be cited throughout this chapter, but readers are encouraged to turn to the back of Synergetics for Loeb's report. Mirrors. There's more to the mite than meets the eye. For figure 13.5 shows a corresponding face of both a positive and a negative mite. As every mite incorporates both a positive and a negative A module, it is the,
hang on, there we go,
unpaired B module slanting off to one side or the other that determines the change of the overall system. From the above,
sorry to interrupt. It's not the shape. It's not
no,
it's charge. In the charge, positive or negative.
Do you want to say that again, or?
It is the unpaired B module standing off to one side or the other that determines the charge of the overall system.
Okay.
Okay, you read change.
Oh, thank you. Thank you.
May I interrupt just
Yes.
1 second for precision? The might are derived. Let's just say this one. If you take the original tetrahedron, the 8 parts are derived from the subdivision at edges of the first tetrahedron, then of the octahedron. Am I correct? Now, if you take the mites, is that you are taking now the three, what you call the orthogonal system at the center of gravity, what Bucky called the three great circles, and subdividing the whole stuff again, as I see here on the IVM. It's just a technique. That's what you see, Fred. So if you take from the center of gravity and divide by 3 perpendicular planes, you're going to have that reduced might in that system.
No, you're going to have you're going to end up with A or B-Quanta module.
Yes, and the might.
Well, the might you would have to reassemble it from the A and B.
Okay.
Because a mite
I just
includes,
wanted to understand the sequence.
yeah, a mite includes the 2 A's and the B. Is that correct?
Okay. Yes.
That is correct, and there are several types of mites depending on what carrier A and carrier B quanta you assemble with.
Cool.
Okay. Sorry to interrupt.
It's okay.
That was,
Perfect.
that was
Perfect.
an important anchor for me.
It's a chapter that deserves each one of us to take the time to stare at the constructions, because it's not so easy, and waving our hand in space and trying, okay, cut this, cut that. I can't. My head is exploding. I can't do that. I have 3D limitations, but and probably some of you are much better equipped with mind's eye to see in 3D, but I can't do it. I have to stare at it for long enough to get a glimpse of what's really happening. But it deserves it. It's easy and difficult to understand. It's easy to understand the concept, but if you want to drill down to the process of subdividing, this becomes a little bit more difficult.
Right on. Okay. You want to continue, Joe?
Sure. From the above recipe, it appears evident that this minimum space-filling tetrahedron is either right or left-handed. This was also evident from our initial generating procedure, subdividing the IBM to carve out the smallest repeating unit with mirror symmetry, which is then split into 2 equivalent mirror image, positive and negative mites. However, a surprising and easily overlooked result of joining 2 A's and a B modifies the above conclusion. An unexpected mirror plane runs through the middle of this irregular tetrahedron that we have assumed must be either right-handed or left-handed. This means that a mite is actually its own mirror image. The positive and negative versions are identical. The slanting orientation depicted in figure 13.5, I guess A, obscures the obscures this fact. However, it turns out that the Mite has two. I can't see.
I'm sorry. I'm doing something technically on this end. Oop, sheet. Oh my gosh. Oh my gosh. I'm sorry. We were on page 222.
You want me to share mine?
Well,
Yeah.
I need to
Two
capture.
isosceles faces, a fact that indicates that the remaining two faces must be identical but mirror image triangles. Therefore, the outside container of the Mite, ignoring the arrangement of its modular ingredients, incorporates a subtle mirror plane as is actually exactly the same shape as its mirror image. That I'm struggling to see, plus A minus B positive, I guess. So it's A positive, I'm sorry, A negative and B positive. Sorry. Yeah, I couldn't, I guess these glasses aren't as good as I thought. Equals A positive, A negative, B negative, figure 13.5b. This extraordinary fact remains that we don't need positive and negative mites to fill all space. One or the other version or both in random combinations will suffice as its own mirror image, and any mite can fill either position, positive or negative. We can conclude, therefore, that two versions are identical. However, Bucky points out that different internal configurations cannot be ignored, for they point to different energy characteristics. Though outwardly conformed identical with one another, the mites are always either positively or negatively biased internally with respect to their energy valving, amplifying. I can't see what that says.
Choking.
Is it? I can't. It looks like a D to me. I'm sorry. Cutting off cutting off and holding. Thank you. That helps a lot. Uh, proclivities. So cubes into mites. Once the A negative and
I think we should,
yeah, go back over.
yes, reflect on what's just been read.
That'll give me a chance to.
A mite actually is a tetrahedron. Am I correct? Am I seeing that correctly?
Yes, that's what they say.
Okay.
Yeah, the property.
Therefore, our earlier question, whether this is space filling, all space filling, is answered. It is not all space filling. There's that Schönhardt polyhedron cannot be filled by mites. And this result is posterior to the publication of those books.
Okay.
So there exists at least one type of shapes that cannot be filled by mites.
What you're just doing a summary statement there, right? Or are you reading somewhere, Fred?
No, I'm not reading.
Okay, good.
I'm just saying. My question was, can mites fill all spaces, all shapes, and as a mite is in fact a tetrahedron with specific proportions, it cannot, because it's been proven that there exist shapes that cannot be filled, be subdivided into tetrahedron. So I was just answering my own question.
Okay, good. Thank you. Okay.
Which is interesting.
How so?
I'm sorry?
How is it interesting?
Well, it's interesting because it removes the universality, the generally accepted universality of Bucky's thinking.
Hmm.
It how to say it? It adds wiggle room to Bucky's thinking.
Cool. Cool. Shall we continue reading, or is it
Yeah, maybe I
more
want
comment?
no, maybe want Fred to expand on that a little bit at some point.
We'll
You
ask
want me
him.
to, you would like to discuss this?
Yeah, I mean, we can come back to it though. It's not.
Well, we can, but what exactly you?
Well, the universality, like how it exactly challenges that.
Well, if Bucky describes his Mite, his geometrical object, built from the subdivision of a tetrahedron into an A and B quanta, and
Right.
the use of chiral of the A quanta with chiral characteristics and the B quanta with chiral characteristics, using the LCD, the two and one combination, the least common denominator decomposition, and he claimed that this shape that he called a mite is the minimum tetrahedra necessary to fill all shapes. This assertion has been refuted. It's proven that it's not.
Mhm.
Therefore, this puts into question every other conclusion that can be derived from this line of reasoning.
Are
Okay,
you sure of that, Fred? Are you sure?
Yeah,
I'm not sure of it. I'm not completely in, but I'm not sure of it. Maybe we will revisit it. Let's progress.
well, yeah, of course we can revisit it, but it's uh, I find this wonderful. I find this wonderful that further study shows that somebody was wrong.
That Bucky
Are
was.
you
Yeah,
are
in
you
this case.
sure?
Oh, he was wrong on other things. His assumption at the time when he wrote Critical Path 1980, early 1980s something, the assumption was that water was only found on Earth because no trace of water had been discovered anywhere else. We have since found that water is present, is nearly omnipresent, nearly present everywhere in space or in spatial objects. So that's always interesting to see that, and
But
that's good.
Bucky's stuff is yes, water, but does it form a structure? Is it structured?
What would that mean?
I
Water
don't
is a
know
Water is
because
water a
because because
structure?
water is a molecule.
yeah, because Bucky clearly says it talks about the A and B quantas in critical path, that
Yes,
they are all space filler in a
yes,
certain combination.
yes, but they're
It
not.
talks about that.
Now
Yes.
we know that
It talk,
now we know that they're not. There's been an object which is called, thanks to Steve that found it,
Schönhardt.
A Schönhardt. It's probably from German. A Schönhardt polyhedron that cannot be filled by tetrahedra.
I
no,
put, I put that in
it
the chat, Manu, and you may have come in afterwards. I don't think you've seen that. I'm going to repost it in the chat. Okay.
Steve, are you talking by general tetrahedra or by regular?
No,
It's,
general.
it's a
We're talking about
special
general
polyhedron.
tetrahedra. Well,
Let me post it.
it's like triangulation in 2D. You don't triangulate a surface with regular triangle. Well, you can, but you cannot triangulate every surface by cutting it, tessellating it with regular triangle. You have to triangulate it with any shape of triangle possible. And
I just put it in the chat, Manu. This is a recent discovery, evidently.
10 years,
10
something.
years.
From memory, but memory from the
But
past is
no,
always
Bucky has never said that tetrahedra on their own fill all space.
Well, he said a
He's never
mite
said
does.
so.
He
No,
says a
he
mite. He
said
says a mite does, and a mite is a tetrahedra. Therefore,
no. The
that
math
a
from what I read
tetrahedra
here,
shaped as a mite would be all shape filling.
no, what I understand here when I read the mite is that a mite is a combination of a tetrahedron and octahedron. The mite is a combination of 1/4 is written here. Calling
Look at page 221.
yeah, I just highlighted here.
Page 221.
Page 219.
What are you reading from page
Page
219?
219 at the definition of mite. Second paragraph. He said, having already split tetrahedra into equal quarters and octahedra into eighths, we skip directly to a unit consisting of a quarter tetrahedron and an 1/8 octahedron.
Back to back.
Yeah, sharing an equivalent triangle, an equilateral triangle face. So it says very clearly that a mite is a combination of tetrahedra and octahedra. And that is very fundamental.
Well, when I look at page 221 on the top, figure 13.5a, which describes a mite, two mites actually, A minus, A plus, B minus, and A minus, A plus, B plus. These two are tetrahedra.
On the B, I see a quarter octahedron there.
The shape, A.
Yeah.
A. Okay.
Even on 13.4, figure 13.4 show it very clearly of LCD of IVM mite. It shows the tetrahedron and the octahedron. Figure 13.4 in the book.
Sorry, which one?
13.4.
13.4 is 13.4.
A little bit just before that one, Steve.
It is right here.
Yeah, but 13.4 I can't see because it's too complicated for me to see.
That one, yes. But you can see the octahedron and then the tetrahedron on that figure.
The one with the resulting one is a tetrahedron.
No, the resulting one, you see a combination where is hash like this.
The aggregate
The one
shape.
that is
The aggregate shape is a The aggregate shape is a tetrahedron.
Yeah, this
yes,
whole
at
thing
the,
is a
heart
tetrahedron.
of it.
The parts of it don't matter because it's the claim is that mites can be all shape filling, and the mite
Okay,
is
no, not there.
The mite is the aggregate shape. It forms
let's
a
go.
tetrahedron, and then we have the Schönhardt polyhedron cannot be filled by tetrahedron. So the question your claim is that a mite is not a tetrahedron.
It's a composition.
As I stare at it, it is.
Yeah, it is a tetrahedron.
Steve,
Yes,
Steve.
sir. Yes, sir.
Can we read again the definition first? Because it's constructed.
I think it's an important point. I'm glad to go back and read it.
Yeah, 219, page 219. It says,
I'm going to read it. I'm going to read it. Mite. Okay. Next, we apply our least common denominator analysis to the isotropic vector matrix. The procedure, calling for progressive subdivision in search of the minimum repeating unit, comes to an end with a unit that can no longer be symmetrically divided. As before, we seek the smallest system that can be duplicated to recreate the whole isotropic vector matrix. A microcosm containing all the ingredients of the macro array. Yes, I keep going?
Yeah, and that would be a fractal, right?
No, because a fractal you would not end up to a point where you can no longer subdivide it. You could be able to subdivide a fractal in the same way to infinity.
Well, when it says here a microcosm containing all the ingredients of the macro array, that's
Yes.
not fractal?
No, what it means is that you have all the components to reconstruct the original shape that you subdivided before.
Okay.
Okay?
And it would not be fractal.
Well, if it was fractal, you would not be able to stop your subdivision because you will
Right.
never reach a point where it's no longer symmetrical.
Asymmetrical, exactly right. Where it is no longer symmetrical or where it is at once asymmetrical.
Asymmetrical and no longer symmetrical is
Exactly correct.
nearly the same meaning.
And here's that second paragraph if we want to
Okay.
continue reading.
Having already split tetrahedra into equal quarters and octahedra into eighths, we skip directly to a unit consisting of 1/4 tetrahedron and 1/8 octahedron back to back, sharing an equilateral triangle face. This unit, which connects the geometrical centers of any adjacent tetrahedron and octahedron in the isotropic vector matrix, exhibits the same threefold symmetry as its two triangular pyramids taken separately. I'm sorry, I don't understand that sentence. I'm going to reread that sentence. This
Okay,
unit,
good.
which connects the geometrical centers of any adjacent tetrahedron and octahedron in the IVM, exhibit the same threefold symmetry as its two triangular pyramids taken separately. I need a drawing. Somebody understand that?
Yeah, I need a
I
drawing.
can show it. I can show it here.
I'm gonna
Okay.
stop sharing and I'm gonna pin Manu to the screen for me,
Okay.
so I will see him big time.
Okay, we can each do that.
Everybody, if you take a second and pin Manu,
Manu,
he'll
pinned.
be big time.
You've been pinned.
Mm-hmm.
Okay. Do you see this octahedron here?
Yes.
Do you see half of it?
Yeah.
Do you see the quarter of it?
The quarter of it is a tetrahedron.
Whatever, I don't know. That is a quarter of it.
Well, the octahedron is composed of two square-based pyramids face to face. Now, if you take a square-based pyramid and cut it in half along any symmetry, you get two tetrahedra. So the 1/8 of the octahedron is a tetrahedron.
Yes.
Okay.
Whatever the case. So I use this, what did I use? That kind. Okay, this white is here. I'm just trying to put it, yeah. So this is 1/4.
Yes.
Yeah. Okay, if I take this 1/4, because it comes to here, there's still an equivalent triangle that is here.
Yes.
So if I take 1/4, sharing 1/4 tetrahedron and 1/8 octahedron, so that's 1/8 octahedron here, and 1/4 tetrahedron. This tetrahedron, if I go to the center of gravity, I can also divide it into 4. One tetrahedron.
Yeah.
Let me see.
Keep going.
Yeah, no, let me show it separately, the tetrahedron. This is the tetrahedron here. I do it in the same color.
Oh, that's almost as fast as Troopy.
Let me just do it in the same color
Okay,
here.
Manu, take your time. It's okay.
This is the tetrahedron.
You're not under pressure.
Okay. If I take this yellow thing, the center of gravity of tetrahedron, we know that is about 1/3. Is at 1/3.
Oh, for regular tetrahedra, yes.
Yes. Of any actual fact. It's not only a regular. If you trace the stuff. So if we take it, if I divide it, if I take this center of gravity and I draw something into it, and that one and the red one from that into it,
Yes.
and another one from whatever into, I'll have quarters. Is
Yeah, that's fine. That's fine.
yes. I'll have quarters. So if I take any, no, not quarters, eighth, actual fact. If I take or six, if I take this top here, I put this button in, that's one. Going through the center of it's starting, the charges are changing, so it becomes brittle at the, okay, like this. And if I've taken from the top here down, if I take this yellow from here through the bases, it will never show.
Okay.
You take
yes.
from one.
You focus on the process. What the outcome of that?
Okay, the outcome of that is that if you divide this tetrahedron into 4,
Yes.
and you divide the octahedron, as I say, into you divide into 8 and the octahedron into 4, and you take one element of it, and then you align to another element of this one that comes from this. On the face where they shared the triangle, you have a mite.
Yes, but your mite can be divided into tetrahedra. Even if it's not a tetrahedron, it can be subdivided into tetrahedra. Therefore, it constructs a shape that can be subdivided by tetrahedra. Correct?
I cannot say that. That's where I have a problem with
You
it.
can say that.
Well, if you look on
Either
page,
either mite is a tetrahedra, or is a more complicated shape, but based on tetrahedra. That is, it can be subdivided into tetrahedra. Yes?
yeah, and it says on page
Therefore,
220,
therefore, it fills a space which is subdivided by tetrahedra. Therefore, it is incorrect to say that it is an all-filling shape, because we now have an example of one shape which cannot be subdivided by tetrahedra.
Where the flaw is in what you say, the flaw comes from the fact that the composition to get the mite does not use integers in terms of multipliers of tetrahedron. It is an algebraic, what you call linear combination.
There's no need to put any numbers in that. Just pure geometry is enough.
Okay, let's. I mean, I came late. I'm not going to.
I admire your desire to defend Bucky's work to the end.
No, we are reading the same sentence, and I'm understanding something different. So I'll defer.
Okay.
I'll defer.
I'm trying to cut and simplify things. If a mite is a tetrahedron,
and it is.
or if it is a shape.
Show me how the mite is a tetrahedron.
It says on page 220. It says mite is a tetrahedron.
Where is it?
I'm going to show you. I'm going to show you.
Yeah.
954.
It actually quotes
Find the Mite tetrahedron to be the smallest simple geometrically possible volume, field, or charge, all space filling module of the isotropic vector matrix of universe.
There it is. Synergetics. It's a quote from Synergetics. We find the Mite tetrahedron.
Yes, but it's not a tetrahedron as close as you say. That's not what he said. Okay.
He says it is a tetrahedron.
Hold on. Let me show you something.
In fact, it is the smallest, simplest, geometrically possible volume field of
Hold
charge.
on. I'll show you.
I put my case to rest. This was a question that bugged me for many years. So that's my take.
This is a tetrahedron. This. In terms of geometric definition.
No.
This has, because what you are saying that is violating the basic principle of duality, which is not possible. This is a tetrahedron.
No.
This is, yes.
I thought a tetrahedron had four nodes.
I mean, okay, this is a tetrahedron. This is one, by definition. He has a concave and convex.
Richard, you're on mute.
Yeah, no, I see that.
Thank you.
No, I'm just putting here one exhibit. A mite is a composition. A mite, as defined here. What I understood.
What is your exhibit?
Yeah. I'm just putting on the plane.
What is it?
It's a tetrahedron.
This is what you call a convex tetrahedron, as opposed to a concave tetrahedron.
Show me a concave tetrahedron. This does not exist. If you put a plane on each face of a tetrahedron, it is by definition convex. You cannot have a line that goes in and out of the same tetrahedron, a straight line that goes in and out of the same of the shape. Therefore, it is convex.
This is a concave tetrahedron.
So this is convex.
No, this is concave.
Convex. Definition of convex is you have a line that goes through it, cannot come out and go back in.
Well, here's actually the definition.
Okay. And this is a convex tetrahedron. This is convex.
It says a convex
It doesn't have four triangular faces.
Yeah, a convex tetrahedron is a three-dimensional shape with four flat triangular faces, 6 straight edges, and 4 vertices.
Yes, that's.
It is the simplest of all convex polyhedra and can be thought of as a pyramid with a triangular base.
Thank you.
I'm just reading.
What you have in your hand is not even a polyhedron.
Yeah.
You have convexity is not a polyhedron. It's a conjugate of it. Polyhedra are in a real, polyhedra are in, okay, I'll give up.
Look, the last thing we need to do is argue on definitions. Definitions are not something to be argued upon. They're something that you need to understand. That's it. Arguing about definitions is a waste of time. Definitions are what you use to base your reasoning upon. So the definition of a polyhedron is important. Definition of a tetrahedron is a specific case of a polyhedron. And the definition of convex is that any line going through it goes only twice through the boundary. One to enter, one to go out. It cannot go back in. The definition of concave is anything that's not convex.
I'm going to put the definition for a convex tetrahedron in the chat. And
a convex tetrahedron has meaning only when it's coupled to another tetrahedron in a relationship. Convexity is the convexity of relationship.
Look, we're
or
talking
concave?
geometry. No, pure geometry, space filling. Pure geometry is a tetrahedron or an aggregate of tetrahedron. Can it be space filling? And we have a counterexample. It cannot. It
Is
cannot be
this
all,
space filling?
it cannot be all
Hold
space
on, hold
filling.
on, hold on. Is this space filling or not?
No. It's
This is not
composed
space
of,
filling.
it's composed of tetrahedron, therefore it cannot be space filling because we've proven, I mean, somebody has proven that there exists a shape in nature that we can conceive of a shape, even build a shape that cannot be filled with tetrahedron.
I'm sorry, Steve. Let me,
Right.
Fred, let me say again. If you take this tetrahedra here, this tetrahedron here, and then you take part of the implied octahedron inside, it fills all space.
No.
Yes.
Well, it's
Okay.
That's what he said. That's what he said. That's what he says in
Manu, let's
yes.
not argue with that. It's been proven there's no more wiggle room there.
No, that is not. It is not.
A Schönhardt polyhedron. You need to look it up and stare at it.
do you know the Schönhardt polyhedron?
I don't need to know the Schönhardt polyhedron.
I think you do.
Let me just shut. No, hold
because
on.
that's
Hold
the
on.
counterexample. That's what proves that Bucky's assertion is wrong.
I read Steve. Definition there. It doesn't say that.
I know, but there's a new discovery.
It doesn't say so. I'm talking about your Schönhardt tetrahedron. It doesn't say so.
What doesn't say so?
What is written here? What is written in page 219 at the paragraph, the last paragraph here, is exactly the definition of the space filler. It is a construction of something that, from part of the concave and convex, has the definition of what you call a space filler tetrahedron between quotes. That's what he said.
Yes, I'm not saying it's not what it says. I'm saying what it says is false. It's been proven wrong.
Okay.
It says that, but it's been proven wrong after it's been written.
Cool.
It's not Bucky who wrote this. It's not Bucky who wrote this book. This is not Bucky's.
So?
This is what Amy Edmondson writes.
Okay, you can keep everybody needs a hero. You can keep your hero intact, no problem.
No, I'm saying, okay.
So, Richard, you seem to be musing on the situation. Do you have a thought?
No, mine's still back to the basics of how we get a asymmetrical tetrahedron out of a symmetrical tetrahedron. And with the center point is where I'm working from as well. And trying to visualize the asymmetrical configurations so that it's one of the edges at least is different length than the other two edges, the other edges. So I'm still at the basics, the primary of getting it into my head and understanding the construction of the Mite.
Yes.
Interesting diagram. They just put in the chat for tensegrity.
It's important to understand, I would say, the process, how it's made. But if we take the process, if we accept the process as something that leads us to quanta A and quanta B, from there, knowing that quanta A is a tetrahedron and quanta B is a tetrahedron, and the Mite being an aggregate of both objects in LCD defined proportion, then we know that the assertion in the book, which says that this is an all polyhedron space filling shape, we know that this assertion is false. since we have a shape that says it cannot be, that has been proven not to be able to be filled by tetrahedron.
Here is Joe found this in Wikipedia, and there are a couple of
It's not a tetrahedron. It's
No,
not.
it's not. It's a Schönhardt polyhedron.
it's a
No,
polyhedron.
but this one is not a tetrahedron.
I know it. That's the point.
Yes.
That is
If it's
exactly
not
the
a
point.
tetrahedron, it's exactly the point that fill the whole space. And
Well,
Bucky has never said that the tetrahedron fill the whole space. He's never said
and
so.
what Fred is pointing out is that since Bucky wrote his book, some people have been doing some investigation and came up with this idea of the Schönhardt polyhedron, which seems to contradict what Bucky said. That's the premise. Nobody's saying
But that's
what?
exactly where we have a problem. I'm seeing something, and you say, show the one in brown. That is there. That one in brown. No, the one that was before, not this black one. It's clearer to me.
I don't understand what you're saying.
So you were showing this from Wikipedia. Go up,
Top of
go
the
back
page.
up a little bit. Yes, that one.
Well,
This thing here is exactly what is been described at the Mite in page 219. Exactly what it is. And that
well,
thing there, and hold on, and that thing there is not a tetrahedron. If
well, of
somebody
course
say
it's
it
not a
is a tetrahedron,
tetrahedron. It's not
yeah.
a tetrahedron. It's a Schönhardt polyhedron, is what it
No, I
is.
don't. Steve, Steve, Schönhardt is nowhere written on this book. I'm reading on page 219
I
at
know,
the bottom.
and Manu, it's just
Yes.
kind of surrender to the idea that somebody in the universe has proposed something that's not consistent with what's on page 219. And rather than resist it, just ponder it.
What is not consistent with page 219 there?
Right
That's
here,
what I'm saying.
Schönhardt polyhedron is a polyhedron with the same combinatorial structure as a regular octahedron, but with dihedral angles that are non-convex along three disjoint edges, because it
Is
is
it
no what?
the thing shown to the right?
Yes.
If it is the thing shown to the right, that thing that is shown to the right is exactly the same thing that is described in page 219.
Well,
No.
Unless you prove me wrong.
No.
well, read
We don't
this.
need to prove you
I will
wrong. You
say
just
this.
need to read the definition and understand by yourself.
I will
That's
say
right.
this. I
Nobody
These
mean,
are,
needs to prove.
these are two different objects.
We do not need to prove anybody right or wrong. It's simply here it is in Wikipedia. So evaluate it. Maybe this guy missed the boat.
well, yeah, I mean, if you look at the year he actually discovered it, and the year subsequent to that,
1928.
yeah, so that's a factor. I mean, that's not as if it were discovered after Bucky. So
Yeah.
My point here, I'm not trying to invent anything. I'm saying that thing there, that is in brown, that is there, is exactly what is said in page 219. At the bottom of it, at the definition of a mite. That's exactly the figure.
Except his properties, non-convex, no interior diagonals, cannot be triangulated. And if it can't be triangulated,
It's
then
it's triangulated in 3D. It's generalization of triangulation.
yeah. So this is just worth pondering.
Tetrahedralized.
Yeah. So
I just have to, sorry to put my final pose on this one, on this issue here. I just have to, I've read what you said. And I repeat, I don't see what is the difference between that and 219. And to say that the mite that you have in 219 is an null space filler. That's all I'm saying.
good. Noted.
All right.
Okay.
Um,
The fact that you can't see it doesn't change
yeah.
the reality.
Okay, good. Now let's see where we are here. Where did you finish reading, Joe?
Let me see here.
You recall?
Yeah, I mean, I do, but
I think it was on page 222.
I don't, a page I don't remember.
You read this,
I'll use it up. Hang on.
right?
I'm not looking at anything, Steve.
Oh, I'm not sharing?
No.
No.
You're sharing Wikipedia.
Oh, really? Oh, wow. Okay, pardon me.
So I definitely didn't read that.
Yeah, pardon me. Although you put it in the mix, young man. Okay, here we go. You read this statement about the
I'm still not saying it.
you read this.
Still got Wikipedia.
And I just want to get through. If we've gotten to cubes and into mites, if we've gotten to here, we're in good shape. I think you read this part. I read that. So if you want to just finish this off.
Yeah, I read that. Okay, yeah.
Yeah,
Yeah, no, that's yeah, I can read from there.
good.
All right, let me give it a shot here. This extraordinary fact means that we don't need positive and negative mites to fill all space. One or the other version, or both in random combinations, will suffice. As its own mirror image, any mite can fill either position, positive or negative. We can conclude, therefore, that the two versions are identical. However, Bucky points out that different internal configurations cannot be ignored, for they point to different energy characteristics. That's like quanta A and B. Though outwardly conformed identically with one another, the mites are always either positively or negatively biased internally with respect to their energy valving, amplifying, choking, cutting off, and holding proclivities. Why do
You know what?
I
You
did
did
read that.
I did
read
read
that.
this. Yeah.
Forgive me. Yeah, keep going. Yeah, I thought, yeah, keep going.
All right, good. We'll finish. We can go down. We can finish this section for sure.
Wait a minute. Now that I think I've had I think I read that section. Hang on.
You
Did
read,
you read cubes and
you,
mites?
Yeah, keep
you've
going.
read until 954:43.
Yeah. I read this.
The
Okay,
proclivities was hidden.
I didn't. Okay.
Did
Go
you
back.
read this? Isosceles
No,
triangle?
definitely not. Definitely didn't read that. Go up.
Okay. So cubes into mites.
Yeah, that's where we are.
Q's.
That's where we are. Okay. Whoop. There we go. Go for it.
Oh no. There it is. Once the A negative and B negative
That's
gain.
A dash B dash.
Oh, I'm sorry.
That's the A module, B module is what he's referring to.
Forgive me.
I think no, you don't. There's nothing to forgive. I think if it were the plus minus, they would be superscripted rather than in the middle of the thing. That's my opinion on the reading. I hope I'm
agreed.
correct.
No, I agreed. That
Okay,
that
good.
is correct. Significant relationships are uncovered at every move. All right, yeah. The game thus becomes more and more fascinating as it is played. For example, we might carve open a cube generating 6 square-based pyramids, one from each face to the
CG.
Yeah.
then
Center of
slice
gravity or the
center of
geometric
gravity.
center. Yeah.
Yes. Then slice each square pyramid into quarters like a peanut butter sandwich. We thereby rediscover the mite, observing that the cube consists of 24 mites, figure 13-6.a, oriented with one of its isosceles triangles, 45 degrees, 90 degrees. On the cube's surface, the mite simply rotates to transform octatrusses into boxes.
Wow. Okay. Oops, where'd it go? This is the little picture. Want to study that for a second. There's the cube. There's the octet trusses. And then the caption on this reads, the LCD of both cube and rhombic dodecahedrons is the mite. the lowest common denominator of both
The
the cube
meaning,
and the rhombic.
the meaning of that is that it's like a power of a prime number. You can reconstitute it with one object only.
Right on. And Joe, you might want to just
That's to cycle back to our start where LCD was
why don't you read about rhombic dodecahedra here, please? And then that'll
Absolutely.
end our reading for tonight. Go ahead.
Sure. Rhombic dodecahedra. Next, we apply the lowest common denominator procedure to the rhombic dodecahedron. Its 12 faces each frame a diamond-shaped valley ending at the center of gravity point. Each of these inverted pyramids can be split into 4 2 positive, 2 negative asymmetrical tetrahedra. Figure 13-6, point B. This is the LCD of Fuller's spheric, and it is none other than the mite. The LCD of the isotropic vector matrix, 48 mites in yet another orientation, make up this space-filling shape. Not surprisingly, space filling and mites have an important connection. No longer caught off guard by such interconnectedness, we conclude by observing that the mite, faithfully representing octasymmetrical
Symmetry.
symmetry, I'm sorry, is also an integral component of the cube and the rhombic dodecahedron.
Good. That ends our reading for tonight. Great. Any comments or questions on what we just read? Wonderful. So let's begin our takeaways. Richard, you've been so quiet and you've been struggling, it seems to me, with the same basic issues that I've been struggling with. So what do you have any takeaways from tonight?
Take away my confusion. As you say, I guess maybe I'm thrown off by what I've been doing with the tetrahedron in terms of being able to fold it up, take the 4 triangles in a 2-dimensional form and then fold them up as in the diagram. And so on, and as you say, the fractaling of them, or the division by the midpoints, can go on for infinity. And to be able to switch over and see the asymmetrical tetrahedron with if I've got it right in my mind, there is one of the edges into the center of gravity that is longer than the others. That's what I'm trying to switch my visualization from sort of, I suppose, 2-dimensional, 3-dimensional into this other dimensionality when you take the 4 faces of the tetrahedron and create 4, in my mind, mini tetrahedrons, but there's going to be some with the longer edges than the others. And then moving that down into visualizing the quanta A and B. So I am well behind the pack here, trying to find a way to catch up and get into the final quarter of the race, so to speak. So that's my takeaway, is my struggle with making that kind of visual sort of transformation. I guess I can go from one silence sort of participant tonight to another one, and invite Lee to see how she's feeling and what her takeaway is.
Well, I feel as though I have fallen into a hole, a dark hole that are filled with mice that are like little bugs. And I haven't yet figured out how to get rid of them. At least I've seen what one looks like, but how it got there is beyond me. I'd have to study it, I think, for about a month or two, or maybe 3 years, to really grasp what all that you have all been talking about. That's all I can say. Fred, hopefully you can rescue me in some way. And how do you feel, and what have you taken away from all these mites?
Thank you, Lee. I certainly would like to rescue you. One way to do it is to sit with Steve and stare at it until a solution occurs. That's one of my math teachers told me that. Stare at it until a solution occurs. And, and this applies to human relations too. It's about being present. If you're present with something long enough, a lot of lights is shed on things. One thing is very important is definitions. Definitions are very important. If you cannot build a good reasoning on imprecise definitions, so it is always very important to go back to a definition whenever there's a doubt about reasoning, a doubt about something. And most reasoning uncertainty resides in shaky definitions. If we can go back to the definition, reread, reformulate the definition, understand it well, it usually solves most problems. And I feel really good because problem of space filling, which is an old 20th century problem, nobody cares about that any longer. This problem of space filling was, as far as I understand, culminated with a peak of nuclear energy, because it was very important for nuclear energy to be able to concentrate material in a shape and in the most concentrated shape as possible in order to minimize the quantity of matter needed to start nuclear reaction. So I think that's where it came from. So the culmination of that was 1950s to 1970s. After that, the problem was solved and nobody cared about it anymore until somebody in the early 2000s discovered that, or proved that there exist shapes that cannot be triangulated. And ever since I read Bucky and I had this shape, I did not know if it which way to go, and today I do, and I feel very good about that. So thank you all for helping me seeing through. Joe, how are you feeling and what is your takeaway today?
I mean, this is interesting. I think this is something that maybe requires a little bit more time to think about. I think that there is, there's obviously it's incredibly significant if it's the minimum space filling object within the isotropic vector matrix. Making it essentially foundational. So kind of fully understanding that is critical. I don't, going back to what Steve was starting to talk about at the beginning with the asymmetrical A and B modules. I thought that was important for this evening. Basically, how mites contain both A and B. And I think that that's a really important point to think about. In how that actually may, and I'm trying to link that to how that Wikipedia Brown diagram actually worked. But anyway, it's a little bit, takes a little bit more time to think about it. Yeah, I agree with you that it has a lot. This is important as far as understanding energy, Fred. And so this is an area that requires a little bit more thought from on my part. But I got to tell you that the really the big thing is the A and B modules essentially are, you know, essentially both. It might both contains both of them. And that kind of is because we talked about the, you know, how the A and B modules are different in shape, but had the same volume earlier in the chapter. So anyway, that's why it was kind of, you know, interesting to me. Manu, how are you feeling? What do you take away from today?
I feel good. I feel queasy. And I have one calculation, simple, that I would like to put to everybody. I read the definition. And that definition says, a unit consisting of 1/4 tetrahedron and 1/8 octahedron back to back. What is the volume of that unit? Is 3/4 tetrahedron. If you add the two. Because all polyhedra that we'll be talking about is about energy measurements. It's about the container of energy, the unit of account of the unit of the cosmic accounting. That's what we are looking for. We're looking for the most efficient.
Yeah.
So I don't understand how 3/4 of something can be that thing. I repeat again, I don't understand how 3/4 of something can be that thing.
Can be what?
Second thing here. Hold on.
What the word?
Please.
Can be what?
3/4 of something. 3/4 of tetrahedron cannot be a tetrahedron. I don't want, I just say I put a quiz. The second thing that I draw in here is that the Mite has been shown to be consistent with the tetrahedron and be consistent with the cube. That is, it verifies the dual definition of something. It abides to the duality principle in that in its function, being able to fill the cube and being able to fill the tetrahedron, it can fill all space. And that's what I take away from this. And my it's not even a conviction, it's only a consequence of this, is that the Mite is an all space filler. The Mite is not a tetrahedron. That's what I take away. Otherwise, I'm grateful and I'm privileged to listen to and participate in the discussions here. And it was this is a process that makes us progress. And that's my takeaway. Who is left? Steve, how do you feel? What do you take away?
I feel pretty good. Part of me wants to take the words out of this book that says the mite is a tetrahedron and show you the picture that seems to look like it, like me. It says figure 13.4. It shows the A and the A and the B. Other than that, I'm excited. In fact, it was exciting to me to find out. Do you want to mute? It was exciting to me to find out that, you know what, I can just do that. That the Schönhardt polyhedron was invented in 1928. And as I listened to Manu like way about these things, I thought of this one of the my visions of enlightenment is to be able to maintain my sanity in the midst of cognitive dissonance, where there's two opposing ideas are out there, and I'm going to hang on to them at the same moment and not blow my brain out, you know. But I also posted down there that there are different kinds of there's cognitive dissonance, and then there's also depending on the context, there can be such a thing as ambivalence, which is just mixed feelings, or doublethink, deliberately accepting contrary ideas simultaneously. So I'm going to double think for a while. I also, what really struck me, and I see how Manu, because Manu has the most topological brain I know and has been through this Bucky tetrahedron convex energy charge thing. If we got into energy charge, I think we'd have another conversation. But just in defense, if there's any defense, I would just like to say this. There have been times in real estate where young kids have challenged me and said, "You're wrong." I was talking about a 1031 tax deferred exchange, or I was talking about substitution of collateral. I was talking about some minuscule, some not very well known idea about the rights of a second lien holder in a transaction as opposed to a limited partner, and how sometimes you can record liens and be a limited partner and have double protection. I remember being in a situation where everybody in the room said I was wrong, and I could not defend myself, but knew there was something we were not considering. And I'm going to hold out for Manu that there is something here that this guy Schönhardt did not consider when he put together his object. And I'm just going to entertain that and see if I even get there. This has been really exciting for me tonight. I'm really excited that we had some controversy, a little bit of like but we're all fine and we're all growing and we're all here together. And I sure appreciate, Fred, your feedback has been real helpful. The fact that you knew about a Schoenhardt polyhedron is exciting. And maybe one day, if I understand what Amy Edmondson is trying to say here, I'll understand better about the Schoenhardt polyhedron. Joe, did you know? Are you trying to say something, Lee? Okay, go ahead and push your.
Did I know?
You muted Lee.
You can't hear Lee.
She's frozen, actually.
No, she's frozen.
Real loud right now, okay?
Are mites slices just slices?
Of what?
Have they slices of whatever?
If you look at the diagram there, a mite is a tetrahedron. It has an A and an A and a B.
But it's a slice.
It's a what? It's a
A
what?
slice. Like
No,
this.
it's a polyhedron. It's got volume.
Oh,
It's not just a slice. Okay, Joe, did you
Yeah.
know that C.J. Fernley commented on the back of Amy Evans's book?
I knew that he knew her well.
Well, there it is. It says C.J. Fernley, Executive Director of Synergetics Collaborative, SNEC, and he's made a comment right there on the back of the book.
I thought of him a lot this, it was December 8th that he passed. and so that'll be next week. And I thought about his last Thanksgiving actually this weekend, and how that must have been tough, obviously.
Do you have a copy of the book with his statement on the back of it?
I don't have. I have
Yes,
a
yes.
PDF or the electronic copy. I do have a copy upstairs, and I could look at. Yeah, I'll have to take a look.
Look at it, and I'll take a picture of this right away and text it to you,
I appreciate
Yeah.
that.
so you have something in your hand. Gosh, I
He's
love
on.
what?
Sorry, are you too tired?
Different cover, Richard.
And one what?
No, I'm asking if there is any American that is too tired.
I'm
Because I
pretty
like to.
tired.
You're tired.
Yeah.
Joe, you tired too?
I'm very tired.
Okay, so for
It's
another
it's
time.
it's midnight for
another,
Joe.
For another time.
Richard,
Okay,
you were holding
let's
up
go
a book. What did you have in mind there, Richard, with your
Well,
book?
I was just showing my book doesn't have CJ's testimonial on the back.
Okay, cool. I'll take a
Mine's
picture,
got
Joe.
Applewhite, Medard, and Anne Griswold, no, Ting, and Havlick.
Wow, this has Applewhite and Griswold and Havlick, but it also has Gable, Fernley, and Baldwin.
Hmm.
I will
Can
take a
we
picture.
can we revisit this thing next week or on Thursday?
If we
Or
want
on
to
Wednesday?
do, if we want to revisit, I don't think it'd be fair for Wayne if we revisited it. Let's revisit it next week. And if you look at the
Yes.
Schönhardt polyhedra and give us some evidence of why Schönhardt maybe have forgotten something when he came up with his design in 1928, I'd love to do it. As long as we
No,
maintain
Schönhardt,
our
I have
equilibrium,
no
I'm a happy
problem.
person.
I have no problem with Schönhardt. I have problem in this book, the use of the word tetrahedron for the Mite. It's not a tetrahedron. It has the properties of a tetrahedron, but it's
Okay.
not a tetrahedron.
Except it actually quotes Bucky, from Synergetics 954.09.
Yeah, exactly. But Bucky didn't call that a tetrahedron.
Well,
He called it a Mite. He said a Mite.
it's called a minimum space filling tetrahedron. That's
Yeah.
what a mite means. That's the definition.
No,
of
in terms of, that's why I wanted to go. You're tired.
Well, bring it up.
You know.
Bring it up next week. Let's talk about it next week.
Yes, that's what I wanted.
Good.
And that's where, to me, that's where the controversy is.
Cool. We'll bring it up next week, and then we'll actually go for a consensus. And if it's a consensus, we continue with the debate. We'll continue. Otherwise, we'll go back to our reading. We're gonna.
Well, I mean, the consensus on this appellation is not necessary. The most important property of it is that it is an all space filler.
Okay. If you want to bring it up next week and provide some evidence,
yeah,
we'll look at the evidence. And
okay.
And then, we'll go from there. I'm excited. Thanksgiving's over. This evening's over, and we're all smiling. So
Yeah.
I'm giving extra thanks. Blessings to you, Fred, and in the next chapter as you complete your ceremony.
Yeah.
I think that's coming up this week, right? You bet.
Yes. It's
So, are you going?
When is
it's
that?
on the 5th.
Are you going to warn us when? At what time exactly, Fred?
It's on the 5th. I don't know what time exactly.
But are you going to tell us the time?
I will send an email. I have the mailing list. Yes.
Okay. Yes.
Thank you.
Because I mean, you appreciate that we are at very different time zones, and you really want to be synchronous to that. You really need to.
We live in a non-simultaneous universe.
Okay, cool. That's what is interesting with you.
All right.
Okay,
Thank you.
see you soon.
Okay.
Farewell,
Yes.
everybody. Bye-bye.
Bye.